Assalamu alaikum. I am Asim Haider and today I am presenting you uh, the lab task in which we are performing logic simplification using K-maps, and we will understand how K-maps works and how we can simplify our expressions, Boolean expressions using K-maps. So first of all, I will tell you about the standard form of Boolean expression. We have two, you can say, three basic form of Boolean expression. First one is sum of product, and the other one is product of sum, and the third one is canonical form, in which we can that is similar to SOP or POS, but we the methodology through which we write that expression is different, and we will take it later. And then we will talk about how we simplify the Boolean algebra, Boolean expression, and how we simplify that expression using K-maps and don't care conditions in K-maps and all that stuff. We will talk about it later. First of all, we will see forms of Boolean expression. Forms of Boolean expression. So forms of Boolean expression. First one is sum of product form, and the other one is product of sum form. In sum of product form, we will have and terms, just like here we can see and terms mean A and B and C. That is one and term, and the other one is D and E and F, and the third one is G and H and I. uh, we can have A and B, that is one term. We can have A and B and C and D with four in a variable. We can have with two variable, we can have three variable, and that's so on. So basically, when we have these and terms and we take sum of that and terms according to our inputs, according to our data, according to our truth table, that will become sum of product form. So basically, the thing is, when we take sum or when we take or of these and terms, when we take uh, some of these product terms, that become our sum of product form. And similarly, in opposite way, we will have a product of sum form, POS form. Similarly, we will have A or B or C, D or E or F, and G or H or I. These terms, when we take product of these terms that are in some terms or that are in or form, so that will become product of some form or POS form. Canonical form is basically a method through which we will write our expression. Let's say we will have a truth table. If here you can say we will have a truth table with three variable A, B, C, and with one output F. So we have to take sum of product form of this truth table, and we will consider min terms. We will take a logic of min terms, and using min terms we will consider one. So you can see what is term for one. For one, we will have a uh, a naught b c, a naught b c, that is and term. We will write it in sum of product form, so we will collect our and terms, and then we will take sum of that and terms. And I am telling you about how we can write in this truth table in canonical form. So canonical form, uh, we have to consider one. Here is we have one at 3, we have one at 6, and we have one at 7. So how we can write and or product term for this one that is placed on 3? We can write it A and B and C. In min term, we consider 0 at complement of that term. For example, if a has 1, so we consider a, or if a has value 0, so we consider it a complement. So we can write a complement bc, and for this you can see that we write a complement bc, and for this one we have a b c complement, because we have 0 for c, so we will write c complement. So here you can see we have a b and c complement, and then we for this one we have all three variables that have value 1, so we will write a b c. Okay, so you can check we have three product terms, and for sop form we will write it a b c, uh, a and b and c, or a, and we will write some of these product terms. Okay, so this is and similarly we can write pos form using max terms, and we will consider zeros, and or we can take complement of these three terms, and some will convert into product form and product will convert into sum form. Why here we have one thing, that canonical form is not efficient. Why? Because it will make our expression so complex. Sometimes it will make it so lengthy, and we will verify this statement that with using canonical form we will have so complex boolean expressions. So this is not efficient way. In digital logic design we talk about that we have to consider the gate cost and circuit cost, that matter in digital logic design, that matter in digital logic design, and that is important. So we will have to simplify our logic as possible as it can. So we can see this is not efficient method. So what we are going to do is that we have to understand k-maps, a terminology that is truly helpful to simplify our expressions. You can check that we have implement this uh, expression here, and with that expression you can see that this expression AB plus BC is simplified as this one, or this can be simplified as this one. So we see that this canonical form gives us a very large expression. So we should consider, and this is pretty simple that we can simplify that expression, but every time we don't have so much time that we are taking a canonical form and then simplify that expression. No, we have to consider a method that gives us directly a simplified version, a simplified boolean expression, that we implement that expression, and we confirm that this is the simplified expression. We don't need to worry about that, oh, this is complex one and we have to simplify that. No, so we will go to that k maps. What are k maps and what are the terminology? This thing, this is a table for three variable k map. Okay, we will consider, let's say we have three variable. You can check here, we have three variable a b c, and we have to make a uh, K-map. K-map is basically a number of uh, grids, and a grid that contain number of boxes, and every box is specified for one uh, integer, one or zero, and we will put that integer into that box. Okay, so we see that for three variable we have eight uh, relations, eight combinations. Okay, so we have eight boxes, and we will write that A for this vertical or this column, and BC for this horizontal or for horizontal row. For A, we have two combination, 0 or 1. Okay, when we have one variable, we have only two condition. It will be 0 or it will be 1. For two variable B, C, we have four combination, 0 0 0 1 1 1 1 0. Here is that we have 0 0 0 1, and after that 0 1 we should have 1 0. Why we don't have 1 0 here and 1 1 here? Because you can see logic here that for every incrementation, we are changing only one variable, either left one or right one. This is not method that we will uh, change the position of both variable. You can check here, we have 0 0, and here only one is changed. It will become 0 1. 0 is same, and from this 0 it will become 1. But if we write 1 0 here, it will become 0 to 1 and 1 to 0. So it will not be our logic uh, that we are following. Okay, so we write here 1 1. You can see it will change from 0 to 1, and from 1 to 1 1 it will become 1 0. And that's how K maps work. What we are gonna do here, we have 0 1. It This one have 2, this one have 3. You can check 0 0 0 0 0 0 1 1 0 1 0. It will have, it is, this box is 2, and for 0 1 1 it, this box is 3. For this box it is 1 0 0. This is 4. 0 1 2 3, and this one is 4. And for this one is 5, this one is 6, and this one is 7. And here in this truth table we have a value of 1 for 3, for 6, and for 7. We will write that values in 3 here, in 6, and in 7. Okay, and we will simplify our expression uh, by making boxes around that, and considering 2 or 4 or 1 in that box, and write that expression for that one. Here is an example that we have an expression A node BC. A node BC means we have 1 for this value, because this is SOP form. Okay, when for filling SOP form we can write 1 for this and term. Where is this and term in this variable? You can check, this one is A complement. A complement, okay, A complement, it means 0. We have this and term in this row. Next we have to check B and C. Where is B and C? This is B complement, C complement, this is B complement, C, this is BC, and this is BC complement. So we have one here, A complement BC, A complement BC, and we write one here. And for this term we will have A, B complement, and C. A, B complement, and then C. We'll write one here, and so on. What's next? We will make a pair. In this K-map, we can make pair of 1, we can make a pair of 2, we can make a pair of 4, we can make a pair of 8. Not other than these terms. Okay, we can't make a pair of 3. So here we can make a pair of these two were, okay, we can make a pair of these, we can make a pair of 8. What we have, you can see we have a lengthy Boolean expression, a complex Boolean expression. We will simplify it using K-map, and this thing can be directly performed using a truth table. That canonical form gives us from truth table. and we can check it from two table. As I told you that we have a number 0 1 2 3. I can write, if we have 1 in truth table, we can write directly 1 here. We don't need this canonical form. This is an example that this example told us about an expression, and we have to simplify that when we are simplifying through k-maps. So what we are doing, we will make k-map, and now we will write an expression using these pairs. Okay, first we will write, we check these one. Okay, for this one, a is remain same. We one thing we have to note down that for two for two variables or for four variable, one we can't say that if we have b here, like b here, b 0 and here is 1, we will not consider b because it is changing for uh, both values. We are only considering that values that are same or that are common for both uh, of the values of a pair. Okay, here you can check a remains same for 1 1, and b is changing, and c remains same, c is 1 and 1. So we will write a and c. Okay, for this one, a is changing, from 0 to 1, so we are not considering a. What we are writing, 1 1. 1 1 is remaining throughout this column, so we are writing bc. And for this pair, a remains same, and that is a, not a complement. A and from b and c, you can check b remains same, but c is changing from 1 to 0 for this box, so we are writing ab. That is simplified version of this boolean expression. So this is significance of k-map, and we are using it for this thing. Here is many example of k-maps, and what are the don't care condition. Don't care condition are like these, that we are given x, that means we don't care what the value is. It can be 0 or it can be 1. It is helpful in this k-maps. Let's say when we have, for example, we have 1 1 1 and 0, we don't know what is don't care. We have to make a pair of these two, 1 and these two. Okay, so we will have two and term, and we will make a sum of product of their two terms. But if we have an don't care condition, we will make a pair of four terms. Okay, and that will become a only one variable, a, because a is not changing for all these values. Okay, so that is simplified version of this k map using don't care. Now I am taking you to the lab task. Lab task is to design a 4-bit truth table for ABC. We will have to make a k map. First we will have to make a 4-bit truth table, and with 4 input, and with 4 input we will have 16 combinations, like 000 001 0010 and so on. And in these 16 combination, we will put 1 for 7 random 7 random combination. We will take an output 1. Okay, that's our choice. We can write 1 for any of these combination. Okay, and we will make a canonical form of that output, and we will simplify that output using k-map, and we will verify that boolean expressions using proteus and using quartus code. Okay, so I write a 16 combination truth table here, a b c 000 001 0010 and so on, and I put one randomly. I place 1 here, 3 on 3, on 7, on 11, 12, 13, 14, 15. Okay, what we have to write I explained you about that. For this one we will have a canonical form of a complement, b complement, c, d. Okay, for this one we will have an and term of a complement, b, c, d, and for this one we will have a, b complement, c and d, and that goes on. Okay, and that we have 7 terms, and we will take some of these 7 product terms, and this is, you can see, we have a very complex boolean expression, and that takes so many logic gates, and if we can simplify it. We can consider that we have to simplify this boolean expression. But what if we implement this result using kmap? So we have 1 at 3 at 7. Here we have a kmap for 4 variable, and we will place 1 at 3. Oh, sorry, we will place 1 at 3, at 7, at 11, 12, 13, at 11, 12, 13, 14, and 15. Okay, and I make a box, make a pair of these 4 term and these 4 term, and you can see for this box what we are considering is just simplified. You can see a and b value is changing for these terms. For these 4 terms a and b values are changing, but b c d value is same. For all these 4 values, cd values are same. So first we have a term of cd, and the other term is, for these 4 variable, b and c and d values are changing, so we will have a and term of ab. Okay, you can see a1 for 1 1, these 4 boxes are paired. Okay, so we will have a simplified version of ab plus cd. Okay, and next I will take you, you can check that what we have in using canonical form, a big complex function boolean expression, and what we have using kmap, a simplified cute little expression, boolean expression, uh, using kmap. Okay, so what next? I am taking you to Proteus file where I implement these function. First function is this one, okay, and the second function is this one. Okay, so we implement it on Proteus. You can see we have 4 variable a, b, c, and d, and we will take a, b, c, d, and a complement, b complement, c complement, d complement using these values. Okay, so we are taking canonical form here. You can see we implement a complement, b complement, c, cd, a complement, b, cd, a, b complement, cd, and a, b, c, d, a, b, c complement, d complement. All these 7 terms, 7 and terms, we write down here. 1 2 3 4 5 6 7. Okay, and for this we make some of these and terms, these product term, using or gates, and for these two we take an or gate, for these two we take an or gate, for these two we take an or gate, and for these three we have uh, these four, 1 2 3 4, we have two or gate, and then we have one or gate and take output. For kmap we have a, b plus cd. Here we have ab, here we have cd, or it moves here, you have to move here. Okay, and we write down a b plus cd, a and b, or c and d. What's next? We will run the simulation and check, is it following our truth table, or a result of both these both these functions are same or not. Okay, so I run the simulation. We check. First we check. You can see we have 0 for 0 0, for we have 0 for 0 0 1, we have 0 for 0 0 1, 0 to 2 we have 0, and for 3 we have 1, and for 7 we have 1, and that's on. Okay, first of all, I will write here. You can check here. We have uh, this is we are. I am opening all these push buttons, and this is 0 0 0. Okay, this one is 0 0 0, and you can see the LED is not turned on. So next, I am writing this is 0 0 0 0. Next one is 0 0 1. No, it is off. Next I have 0010. So 0010, it is 2 in decimal, but again LED is turned off. Next one we have 0011. Now you see that we have one for 0011, and let me check that LED turned on or not. So 0 0 1 and 1, and you see that LED glows. Okay, so this is how it is working, and you can say for 4 it will not turned on, it will turned off. For here we have 0 1 0 0, and LED turned off. For 7 we should have LED on, so it is on. And for now on for 11 12 and similar, the LED will turned on for both these value. So the result is, for both these expression we have a complex uh, canonical form expression and K-map reduced expression, and both are performing the same function. So why we need so much gate and so big circuit and all that stuff? We don't need that. We have a simplified, a little small cute function circuit. Okay, now we have to implement this on Quartus, and this is really very simple. We just have A B C D for input, two output F1 and F2. F1 is for canonical form and F2 is for output form. So for 0 0, we have F1 and F2, and we just simplified all these values, and we write down for F1 and F2. Now I will take I will write some. So first I will show you the RTL view, and we can check. We have that simplified version of F2 here, and for canonical form we have these gates, and we have F1. Okay, for now I will move to uh, university program VWF. So waveform we can create uh, the output waveform. So I am inserting nodes and node finder. We will go to the list, and that's okay. Okay, so for A I will change the waveform time period, and I will must write 25, and for B I will write 50, for C I will write 100, and for D I will write, sorry, I write it in wrong, 25, 50. Okay, 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 okay. So for D we will write it 200. Okay, now I will run the time simulation. Yes, and we will check that we have a same waveform for F1 and F2, uh, because we perform the same functions. Okay, we will verify. You can see that we have one for 0011, that is 3, and 1 for 0111, that is 7, and for 11, 12, 13, 14, 15 we have 1, and we have same waveforms for F1 and F2. That's all. So we concluded that we have same outputs using canonical form and using KMap, but KMap is so easy and so simplified that we don't need so many uh, gates and so many complex boolean circuits, boolean expressions, and that circuits. Okay, so that's all from my side. Thank you for watching, and if you have any query, please comment down. Thank you so much.